Well, good afternoon, good morning, everybody. I'm Jason Russell, help with marketing here. It's time to get things started. This is, you could say, our first transatlantic webinar, as Rich Benner is in the UK. He's in Leicestershire, and that makes it a little bit late for him, 7, right? Uh, he doesn't, as far as I know, he doesn't have a pint close to hand, but he did brew a cuppa, so he'll be on top of his game. So with that, we'll turn it over to Rich and we'll get started.
Hi, welcome to the webinar. My name's Rich. Let's get started. So today we're talking about indexing in SQL Server. We'll go through we'll explain everything, what indexes are, what benefits they have, what drawbacks they have. Hopefully by the end of the hour, you'll have a bit more knowledge about the internals of SQL Server and how you can make your environment a bit better. So who we are, we're SQL Solutions Group. We're a full service SQL Server consultancy, led by Randy Knight. He's a Microsoft Certified Master. Long story short, if you need anything SQL Server based, get in contact. We can definitely help. My name's Rich. I'm a senior consultant at SSG. I've been in this career for 15 years or so now. I specialize in performance tuning, and I'm a massive nerd. So this is a brief overview of what we're doing. We'll go through understanding indexes, what type of indexes they are, all the benefits, best practices, downsides, and some specialist use cases for a few indexes towards the end. Let's just jump straight in. So, indexes in SQL Server. Long story short, it's a structured way of retrieving your data nice and quickly. It's similar to an index in a book. If you get to a book, you want a particular chapter, you want a particular subject, you go to the index, find where it is, and you can get to that information faster, rather than having to look through the entire book to find what you need. Indexes, they store a subset of your data. If they're a non-clustered index, most indexes store part of your data, not all of it. The difference, the only exception to that is clustered indexes, which we'll cover in a second. It's worth noting, when I talk about indexes and I talk about the hardware requirements and the physical requirements of an index, which is storage, reading from disk, storing in memory. All indexes, if they're used by SQL Server to read data from, will be stored in memory when it needs to read the data. One of the things we'll talk about is being as strict as possible as you can be with your indexes. The reason for that is you've only got so much memory on a server. You can't load multiple copies, or most people can't load multiple copies of their entire database into memory and store it there. It's just not viable. So we'll go through understanding how that works, how it gets poured into memory, how it gets stored, and why we need to be careful with what we're doing. So, as I mentioned, there are a few different types of indexes, and we'll go through them in the next list. In the next few slides. But we've basically come down to clustered and non-clustered indexes. That's the primary two indexes you'll see out there. The other ones are subsets of or specialist use cases, and we'll go through those. So, what is a clustered index? You've got two options when creating a table. You can create it with a clustered index, or you can create it without one. It's a binary choice, one or the other. If you don't create a clustered index, it's what we call a heap table. Now, what that means is the data is stored on disk, however SQL Server wants to. If you insert some data into that table, you'll ask SQL Server to store it, and SQL will go, okay, I'll find the next available space on disk, put it there. It doesn't matter where that is. What that means is it's nice and fast. You could throw data into a heap table. The problem you'll have is when you come to retrieve that data, you ask SQL Server, I want some data for this table. It doesn't know what data you want necessarily. It doesn't know where that data is. It returns the whole table, but it also does that from all over your disk. Those of you who are old like me will remember disk defragmentation that we used to have to do in Windows XP. It's basically that. It will be stored all over the disk. What a clustered index does, if you create a table with a clustered index, is you create a clustering key. Now that could be a primary key, it could be a non-unique key, and we'll cover those in a minute. But basically what you do is you say, I want to store this data sorted on this field or multiple fields. And that fundamentally changes how the data is stored on disk. SQL Server will, when the heap's rebuilt or when it's created, sorry, the clustered index is rebuilt or when it's created, SQL Server will take all the data, it'll sort it based upon your clustering key, and it'll store it all neatly together on disk. The advantage of that is when you want to come and read the data, we'll be using some examples, the Stack Overflow database later on, which is the database that sits behind stackoverflow.com, the question and answer website. If I go to the users table and want information on Rich Benner, and I've indexed it on Rich Benner, what will happen is instead of having to give me the whole table and go, well, here's the whole table, find the bits you want, it can go, okay, I know exactly where the R's are and probably the Riches are and the Benners. And it could just return me the data that I need. So that instead of returning millions of rows of data, it returns a handful. There's not many Rich Benners in the world, especially on the Stack Overflow database. I think there's 6 rows of data that get returned. And we'll go through some examples. But just to visualize what that looks like, data on the left here, this is effectively stored without a clustered index. So on the left is a heap table. It's stored on disk randomly. There's no sorted order. So imagine looking through that for display name Rich Benner. It's going to be tough. You'll have to scan the entire table, which is slow. On the right, you can see this is the same table, but with a clustered index on display name. And you can see it's sorted in display name order. And behind the scenes, some statistics will get created, and we'll talk about that in a second. But basically, if I'm looking for the R's, it's alphabetical. I know I can ask SQL Server and it knows where the R's are, and it'll just return the data a lot faster. The downside of a clustered index, and it is the strength of a heap, is when you're inserting data in. For a heap, it just goes in. For a clustered index, if I'm inserting a new user, if I create a new username of Rich Benner with a different account ID, it has to find where I go in the table. It goes down to the particular data page where the data is stored, and it inserts a new row into there. If that data page is already full, it will cause a page split, and we'll cover this again in a minute. But basically, you have to search the data, find the right place, insert it, do some page splits maybe. It's more work to insert. Nowadays on modern hardware, it's not so much of a problem. It used to be a big deal, but it's more work to insert into, but with greater benefits of reading the data. So it's a balancing act. There are some use cases where you definitely go with a heap table. If you're throwing a lot of data into a table, and by a lot, I mean hundreds of thousands of records a minute, you go with a heap. But you'd be aware that if you're trying to read that data from the table, you're not going to have a good time with it. So that's clustered indexes versus heaps. But what you can also do on a table is create non-clustered indexes. Now, these don't change the structure that your data is stored on disk. You can create a non-clustered index on a heap table if you want. But what this does is you create an index on a field that you're using in your queries. So in the previous example, display name. I might index display name if I'm constantly looking up people's reputation, for example, based upon their name. I could create a non-clustered index on the display name field and have an included field which will return their reputation. Now it's worth separating those two fields because it's those two groups of columns. You can have indexed fields, which could be one, which could be many. And that's the order in which your data is stored in this index. You can then have included columns, which are just along for the ride. So you're not searching using them, but you do want to return them as part of your query. You can do that. So in this example, and we'll go to an example. At the top here, this is my query. I'm looking for a guy called John Skeet. He's got the highest reputation on Stack Overflow. I'm searching, my predicate is on display name equals John Skeet. And I'm returning display name, but I'm also returning reputation. Now, if there was no index on the table, which helped me here, you can see on the left, it takes 208 milliseconds to do that query. And bearing in mind, this is on my laptop here, which has an M2 drive, which is directly attached. If you're on in the cloud, or if you're on any sort of array, it'll take longer. This is the fastest you'll see within reason. So it takes 208 milliseconds and it does 86,000 reads. Now, what a read is, and please ignore logical versus, you'll see physical sometimes as well. What a read is fundamentally SQL Server stores data in pages that are 8K large. You'll never see that as a user unless you go crazy with a hex editor and look at and dig into the data files. But that's how it stores data in pages with 8,000 bytes. Each one of these reads is a page. So what we're saying here was we're reading 86,000 pages from disk. And what that means is we have to read that off disk, we have to bring it through the network, and we have to store all that in memory in order to do this operation. On the right here, I created an index which is on display name and includes reputation. It completes immediately, and it does 3 logical reads. Now, the way you can see how many logical reads you're doing is at the bottom there. On your query, for the first line in your transaction, you could put set statistics time IO on, and then run your query. And that will give you a lot of useful statistics, including these. It'll output into the message tab in Management Studio. If you're ever curious what tables a query is reading, how many pages it's reading from those, how long it's actually taking, then set your statistics on and get your messages tab. If you're having problems reading the stats because it's a lot of information, then copy that and paste it into statisticsparser.com. It's a tool created by Richie Rump, which formats it nicely for you. You can see for each table how many reads you're doing. There's so much more information in there. That's a whole webinar in itself. But that's where I'm getting this information from the set statistics on. These 2 queries I ran them side by side, by the way, which is why on the query 1 you can see 100% of the cost for these 2 queries was query 1. 0 of it was from query 2. It's just much more efficient to read the data this way, and you can absolutely apply this in your own environment. Similar queries. We'll talk about this a little bit later as well. So let's move on to unique indexes. Now, the clustered indexes and non-clustered indexes we talked about before can also be unique. You can also have a unique constraint on its own. Basically, what that does is you say, I'm going to choose this column or this group of columns. I want it to be unique. And what that means is, let's say, using the 3 examples of the query we just looked at, account ID, display name, reputation. I don't want those 3 there's no chance those should ever be not unique, because, well, account ID will be unique. So you could create a unique index on account ID. And what that will do is if somebody tries to insert a duplicate value into that, it will throw an error. Now, because you get errors, you'll have to be aware of this when you're writing queries. You'll have to speak to developers. You'll have to let them know that there's some logic here. If they're .NET, you'd have to do try-catch blocks, etc. But it will just enforce that at database level. You cannot create duplicate indexes of this field or these groups of fields. If you create that, a unique constraint on a clustered index, Then we create the primary key for the table, and it's instead of just creating a clustered index, you create a cluster primary key. And again, that could be one or multiple columns, but that's what it's called when you do it to a cluster. For a non-clustered index, it's just when you do your creation script, there's a unique in there. Create unique non-clustered index instead of create non-clustered index. It's a very simple change, very useful for data control. Okay, so filtered indexes. These can't be clustered. These are always non-clustered indexes. And effectively what it is if you're querying data, on the creation of the index, you can add a where clause. Say you've got an orders table in your environment that contains your history of orders since forever. You've got 5 years worth of orders in here. Orders are constantly being modified, being sent out, and you're constantly querying for open orders which aren't in a status of closed. Then what you can do is you can create a filtered index where status is not closed. And what that will do is instead of containing all the rows in the underlying table, it will only contain the relevant data. That could be useful for things like orders. There's many other use cases, but it's a way of reducing the amount of data you're searching through in order to make your queries more efficient. Your read queries, your select queries. There's a few gotchas with filtered indexes. If you are declaring a variable with that I want to return a top 1,000, or in my example where reputation is greater than 10,000, if you declare that as a variable and use a variable in the query, it won't work. It has to be an explicit value. The way around that is by creating it in a block of dynamic SQL, which again we won't cover here, but you effectively push a predicate into the SQL and execute the block of SQL with the explicit value in there. So 10,000 rather than at reputation. We've got an example of it. So here at the top is the query. I want to return the display name and reputation of all users where reputation is greater than 10,000. And I also want to order it reputation descending. So I want the people with the highest reputation at the top of my list. Now at the bottom, you can see the index that I created here. And it's indexed on reputation and includes the display name, because we're not searching using display name, we're searching using reputation. That's the predicate. So that's what we want to index. We're just returning display name. It's along for the ride. We can just include that in our index. But the filter looks for reputation is greater than 10,000. Now, on the left here, you can see the duration, 280 milliseconds, and it does our 86,000 reads. That's the whole table. It's scanning the entire table. And if you look at the execution plan, if you're not too familiar, on the right of this execution plan, you can see our table scan, and that's scanning the entire table. We're then having to sort the data because I've asked for it descending. So we have to sort it. And then because it's such a big query, it went parallel. So we have to gather the streams before we return the data. Now this, of the two, was 100% of our query cost. And we'll cover this later, but you can see in green, there's a non-clustered index it's asking for, which is going to improve the performance by 92%, it thinks. We'll come back to what that green bit means. But I created this index, and now we just do a scan, and you can see the index name here. We just scan that index. Now, it's exactly what we want. I've used a hard predicate, and it's already sorted. Now, it doesn't matter. The index is sorted ascending. I've asked for it descending. Doesn't matter. As long as it's sorted, SQL can do a read from the end on the index as well as a read from the beginning. So that doesn't actually matter. But you can see again, on the left, 86,000 reads, on the right, 60 reads to return all this data. That's just much more efficient. It's less disk, less memory, less IO. It's a no-brainer when it comes to select queries. although there is a balance, and we'll talk about that later. So if you can use filtered index to solve a particular problem, absolutely bear that in mind. Okay, next type of index we'll talk about is column store. Now, most indexes are stored at a row level. So you insert a row of data, it stores it as a row of data. What column store does is fundamentally stores that differently. Now, you can create this. I mentioned clustered indexes earlier. You can create a clustered column store, which again fundamentally changes how your data is stored on disk. You can also create non-clustered. But what this means is the way the data is stored is it creates row groups. When you create a column store index, it creates row groups, which is roughly 1 million rows of data. And what it does is it takes 1 million rows of data and looks at each column and tries to compress them. This is great if you've got a lot of repeated data. We go back to the orders table. You've probably got item number or barcode number or anything like that, an item identifier. You've probably got a price. You've probably got a status. Those, you'll only have a certain amount of those. They will compress really well. I went to a client not too long ago. When I went in, they had a history table, which contained a history of data going back a number of years. It was 450 gig. I applied a cluster column store index. It took it down to 14 gig. As long as your data is compressible and you can take advantage of this, it's a fantastic tool for certain situations. Now, the downside of this is that it's more difficult to access the data you need at times, and inserting new fresh data in there comes with its own idiosyncrasies. Now, what it effectively does is when you either create the column store or when you rebuild the column store index, you'll have a fresh set of row groups. It'll take everything, it'll sort them correctly, and then it'll group them up, and you'll have however many row groups for your volume of data. Any new data that gets inserted into there, that gets updated, that gets deleted, goes into what we call the delta store, which is effectively kind of a sub row group of uncompressed data. And that'll sit in there until you rebuild the index, until you do some sort of maintenance, and we'll cover maintenance later. But for fresh data, it won't take advantage of the column store until you do a full rebuild, which is not a free process to do in SQL Server. And that's not a monetary term. That's a hardware and CPU term. Rebuilding any sort of index comes with a cost on hardware and resources. It's worth noting that if you do very large inserts, and you're inserting more than 1 million rows, it can create a brand new proper compressed row group and just put that in. There's edge cases. But yeah, there's gotchas with it. It's very useful when used correctly. It's something we've used extensively here at SSG. And if you come across any of these indexes and you get into trouble, or you're not sure, or you're coming across some of these gotchas, stuff I might not have even had time to mention in this hour, then by all means, just reach out to us. We're always here. We're always happy to help. We're very nice people, I promise. So yeah, this is column store indexes, usually used for things like data warehouses, where you're loading in loads of data overnight, or you've got a lot of history. Very useful in the right circumstance. Okay, the last index type we're going to talk about is full text. Now, full text is its own beast. It's special when we come to indexes. You have to create in your database a full text catalog, and that catalog contains full text indexes. But basically what it allows you to do is to search text more efficiently than not having it. One thing it's also good at, it allows for indexing of these large types. You can't index a varchar max field traditionally. You have to do a full text index. It's worth noting that basically what it does is it takes all the words in your field and separates them out into tokens. And then you can search based upon the individual word from the beginning of the word. So if it had me in there, it had Richard Benner, SQL Solutions Group, 5 separate words. I could search for solutions. I could search for SOL and a wildcard, and it would find it. I could search for GRO and a wildcard, and it would find it. What I couldn't do is search for ARD, which is the end of my first name with a wildcard. It just won't search for it. You have to search from the beginning of the word. They're very easy to have problems with. Most of the things I've seen with full text indexes is when there's problems and it's corruption. But that can be dealt with. But if you must do a search based upon a large object type, so the text, varchars, image, var binaries on the screen there, then you'll have to consider full text indexes. It's worth noting it does take some time when new data is inserted for it to get indexed, so it's an asynchronous update. So if I insert some data into that table with the full text index and then instantly try to search it, it's not going to be there. It's asynchronous depending on your workloads and the spare resources of SQL Server. So that's something to think about as well. It's not always 100% up to date, but it doesn't need to be in a lot of situations. And again, full text indexes, most of these indexes I could talk about for hours, but if you come across something weird, if you're applying these, reach out, just let us know. We're happy to help. So other things to consider with an index. I've mentioned about memory, and what happens when you read these data, just to go over it briefly again. When you read these indexes, it will be you're reading in that data into memory. You only have X amount of memory on your server. Let's say you've got 100 gig of memory. If you're loading in a lot of 5 gig indexes, they're all going to get loaded into memory. They will persist in memory until your memory is full, and then SQL Server tries to pull in more data, at which point it will take your oldest pages in memory and send them back to disk. Reading from memory is fast. Reading from disk is relatively slow. So you want to have as much relevant data in memory as possible to see the best performance improvements. If you've got a lot of big indexes, a lot of poorly designed indexes, you could be cycling data into memory and out of memory quite quickly. You may have heard of page life expectancy as a statistic in SQL Server. That is the amount of seconds that SQL Server expects itself to be able to hold data in memory before it has to flush it back to disk. So you want to be efficient with how you're using it. It's also worth noting for every statistic you create, there isn't, and you don't have the setting of auto create statistics disabled. It's on by default. As long as you haven't turned that off, then every index will get a statistic behind it. And what this is, SQL Server samples the data that's in the table and creates a histogram, which is like a horizontal bar graph, which will show it will help itself understand where the data is, how your data is laid out. If you've got much more data of a certain type in there, it'll know. Statistics is what SQL Server uses when it decides to create an execution plan and when it's trying to work out the best way of executing a query and returning the results to you. There's some problems with this. So statistics, there is an auto update statistics setting in SQL Server, which will be on unless you've turned it off for some reason. The problem. Sorry. My microphone turned itself off. So statistics get created when you create an index or rebuild an index. It will refresh your statistics. Alternatively, when you hit a threshold, which is, I believe, 10% of data that's changed, SQL Server will rebuild your statistics. Between those 2 points, SQL Server doesn't have a histogram or any information about how your index has been created. Sorry, not how your index has been created, how your data is laid out within that index. That's accentuated perfectly by the ascending key problem. So what that is, imagine you have a table with an identity column as the first column, or as any column, which is an int value that increases by 1. When you insert a row of data, it increments by 1. So I've got a million rows of data in my table. I rebuild the index or create the index. SQL Server takes those million rows and it knows the layout of the data, where the data is, how much data is in there, what types of data you have. I then insert, I spend 2 months inserting data. I insert another 5,000 rows, 10,000 rows, whatever. Anything up to 100,000 rows will get inserted, but the statistics won't get updated for those. So I'm inserting, let's say, order data again. I'm inserting data into the table about my orders and I'm updating it. And then I'm querying that data, but SQL Server doesn't know the layout of that data because it hasn't updated its statistics. So it can make terrible decisions on how it's going to return that data to you. We'll talk about maintenance later, but basically you want to be a bit more proactive in the updating of those statistics so that you can get the best execution plans that you can. One thing I briefly mentioned was the use of indexed and included columns. Now, if you're querying on reputation greater than 10,000 and then returning multiple fields, including, let's say, a varchar max field, notes, or a question ID, you're joining to another table. You've got 2 choices here. You could create an index on reputation and include all the other fields. What that's going to do is increase the size of your data, your index, which increases the size of storage on disk, the extra work your IO subsystem is going to have to do, the extra memory is going to be stored. If not every query is using these other columns, these extra data, you need to decide whether you should include that or not. If you don't, you'll often see a thing called a key lookup or a RID lookup, a row ID lookup. And what that means is it's not necessarily a bad thing, but what it'll do is I'm only going to index reputation greater than 10,000. Now, one thing to note, in any non-clustered index, if there's a primary key on the table, that is included in your index. It's hidden in the background. It's there. So what it'll do, what I'm doing is I'm querying for users with greater than 10,000 reputation. And then I want to know their name, their user ID, their account ID, their country, any other fields. If that's not included in my index, what SQL Server will do is go and look at my index. It'll search down for John Skeet, and then it'll do a key lookup. It'll take the primary key of the table and go and take that and loop around and return the data it needs. It'll have to hit the clustered index again, or the heap table again, to return the extra data. Now, when you have a key lookup, each of those additional fetches is effectively 3 times as expensive. It takes 3 data pages as a rough estimate. Which, if you're doing that a lot, if you're doing key lookups on 1 million rows, that sucks. If your table's 1 million rows, but you're only searching for 4 rows and doing key lookups, maybe you go for that. A lot of the indexing stuff that we'll talk about and we will talk about next is an art more than a science. But it's a case of trial and error and working your way through it and seeing what works best in your environment. What we'll probably do is take a second. Jason, have we got any questions in yet before I keep talking?
No questions at the moment, Rich.
Perfect. I love the sound of my own voice. Okay. So let's just go into why. We'll just carry on through. Why would you use indexes? What are the benefits? So it obviously, I say obviously, it drastically improves the performance of your reads. When you're selecting data, when you're joining data, indexes are fantastic at giving you massive speed benefits, as you can see from the previous demos, the previous data I've shown you. If you do indexes correctly, you'll get much more efficient use of disk and IO and memory, all of these other systems which may be your problem, maybe the network guy's problem, but you can make everybody's life easier by doing indexes properly. Yeah, we've talked about unique indexes. You can force your data integrity through there. You can efficiently sort and group data. We've shown the sorting on the reputation. This data was stored how I wanted it, so we didn't have to sort it. And sorting is expensive in SQL Server. It costs a lot of CPU to sort data. Yeah, text searching, and one thing we haven't talked about is foreign keys. And what a foreign key, I'll briefly cover it in case people don't know. You've got table A, which is a list of orders. And then table B is a list of warehouses that may be fulfilling the order. I don't want to be able to insert data into my orders for a warehouse that doesn't exist. So what I do is have a warehouse ID column in my orders table. And then I want to point a foreign key to my warehouses table to make sure that that warehouse exists. If not, it'll throw there and go, no, you can't create an order for a warehouse that doesn't exist. Now, what happens behind the scenes is SQL Server will go and do a scan of the warehouses table and look for this value. And when it finds it, it'll return it. Grand. Now, if there's no supporting index, we're scanning that entire table because SQL Server just doesn't know whether it exists or not until it checks all the records. If on the warehouses table, we created an index on the warehouse ID, then we've got statistics for that. We've got a histogram. It's much better. It'll go and it'll find that the result much faster than doing a full table scan. Even better if you can have it unique. Warehouse ID in the warehouse table is probably unique. That'll improve efficiency even more. So indexes can give you benefits that are outside of just reading the data. When you're inserting data, it can force the foreign keys to just perform much better. There's other examples, but that's a great example. Now, there are some gotchas and some drawbacks to indexes. If I've got a table which has 20 columns, and I've got 20 separate indexes, I index every column. What I'm going to have to do every time I insert some data to that table, I have to insert to every index, which also contains this data. So instead of doing one insert onto the table, I'm doing an insert onto the table and also inserting into 20 additional indexes. This is a problem that we see a lot with over-indexing, and we'll talk about that in a minute. But it can, because you have to write to multiple places, it can degrade your write performance slightly. It's often greatly balanced with a great read performance, but more indexes doesn't come free. There are some things to think about when we talk about write performance. I've mentioned maintenance, and there's a few things that you should do as part of your maintenance. Later on, I'll suggest a maintenance solution, and we'll talk about that. But the problems you want to fix with maintenance is over time, your data is going to get fragmented, just like that heap table with data everywhere. Any index over time is going to fragment. As you delete data from that index, you insert fresh data into it, you update data. in the index. It's going to fragment. And there's not much you can do about that other than reorganizing or rebuilding the index. Also, the statistics. We've talked about this, but they can fall out of date. And you want the most up-to-date statistics, because then SQL Server and the query analyzer, the query optimizer, will come up with the best plan when it comes to how it's going to execute a query. And one thing you should do, and again, we'll talk about this, but we should do ongoing index analysis. We work with a lot of clients where we go in, we run a few tools. I'll talk about some of them later, and start with indexes. And they may not be in the ideal place because nobody's done the index analysis before. But what we can't do is go, this is what you need to do it, thank you very much. We either do it ourselves or we work with the clients to revisit, do another index analysis in a month, in 2 months, in 6 months. Because index requirements change, your data will evolve. Chances are the queries that you're writing against the SQL Server will change, will evolve. So it's an ongoing process, index analysis. And again, we'll talk about that shortly, but it's extra work to keep on top of your indexes. It's very valuable work, and it's work I would heavily suggest you should be doing, but it is time out of your day. And extra disk storage. If you create, every time you create an index, it creates a copy of the data that's stored in your table. If that's a large field, then you're creating a copy of a large field. That takes extra disk. Now, nowadays, that's not so much of a problem. Disks are cheap when it comes to, when you think about your SQL Server licensing costs, your memory costs. If you're in the cloud, your hosting costs. Disks are relatively cheap and relatively fast nowadays. But you are causing extra storage requirements when you're creating these indexes. So with those in mind, when we talk about index design and best practice, you want to be as careful as you can and as strict as you can with indexes. Now that's both in the context of the contents of each individual index, but also the total count of indexes that you have. So when you're creating an index, you don't just want to index one field and then include everything else on the table. That's often not efficient. You'll have these great big, if you're doing that, you'll take an entire copy of your table. You're storing the same table twice. And if that's a gig of data, you're storing 2 gig of data. If it's a terabyte, you're storing 2 terabytes. You want to be careful. You want to create them as tight and as focused as possible, but that meet your needs. But then also, going back to the write performance, you don't want hundreds of indexes on a table, because chances are a lot of them will be unused. And then every time you have to do a write operation, you're having to do it 100 times. And that's just going to suck for everybody. You don't want to do that. The way you want to identify your indexes is, when you consider the indexed fields, it's fields where you're doing predicates. And when I talk about predicates, it's something in your where clause, where display name equals rich banner, where reputation is greater than 10,000. It's also things in your joins. If I'm taking the users table and then joining it to the posts table in the Stack Overflow to find, for me, all my posts, I'll select username, display name from the users. I'll join to posts, and that will be on account ID and owner ID. I want to join. I want those 2 fields to be indexed if I'm doing that a lot, because otherwise, if it's not indexed, I'm scanning one of those tables. If the if the posts table doesn't contain a supporting index, I'm scanning the entire post table, and that table's huge. Whereas if we had an index based upon owner ID, the join is going to be much more efficient. We're going to pull less data back. We're going to pull back a subset of the table and just get what we need. So that's where you're going to want to index stuff, where you're using that field, not just presenting it back in the select statement. When you're thinking about indexes, you definitely want to be thinking about your index types and what's appropriate. My personal default is to cluster tables. There's very few use cases I've seen where having a heap table is the correct answer. They do exist, but they're rare. But then, do you need to, if you're creating non-clustered indexes, would a filter help here? Should I be clustering? Should I be using a column store here? Does this need to be unique? You just need to think about all the options and what's appropriate for your data and your use case. Yeah, you want to go in there and regularly monitor and tune your queries. Now, that doesn't have to. That's dailies, not what I'm talking about here. But weekly, when you first start, monthly, put it in quarterly. Spend a couple of hours every quarter. Run the scripts, which I'll talk about in a minute, and see, like, have I got any indexes which are no longer used? I can drop those. That will save me some effort. That'll save me some storage and some writes. Have my queries changed? Do I need new supporting indexes? And just go through that process on a regular cadence, whatever works for you. One thing that I haven't talked about here is fill factor. Now, going back to the 8K data pages that SQL Server stores data in, by default, the fill factor is 0, which is equivalent to 100. What that means is when you rebuild an index, it will fill every 8K page 100%, which is the most efficient way to store it on disk when we're talking about the amount of disk space that a query uses, that an index uses. Now, the problem comes if I want to insert data in the middle, SQL Server will come and find the page, and it'll have to take that data, split it in half, it's a page split, and then insert my data. Because there's no free space to insert it into. Fill factor, you can set it to a percentage figure. Let's say 90%. What that means is, next time you rebuild your index, SQL Server on each of those pages will leave 10% of it free, so you can insert some data into there. It does mean that your index is going to take 10% more space on disk because you've still got the same amount of data, you've just now got gaps in it. Now, I haven't actually seen performance issues resolved by changing a fill factor. There's often other things you can do, but it's worth knowing what fill factor is and what it means for you. One thing you don't want to do is go for a fill factor of 10, for example, because what that will mean is when you rebuild your index, all of your data pages are 90% empty. Your table is going to take 10 times as much storage on disks than it would otherwise. And that means when you're reading that data from disk into memory, you're reading 10 times as many data pages because most of it's empty, but you've still got to read those pages. So usually fill factor, you leave it as 100, but be aware that you can change that if you find a use case for it. Okay, index maintenance. Now, we've talked about indexes becoming fragmented and statistics going out of date. So what we recommend is to schedule some index maintenance. Now, there's a fantastic script out there by a guy called Ola Hallengren. It's called Ola Hallengren's index maintenance solution. It's completely free. You can find the GitHub for it. Just Google Ola Hallengren. It'll be the first result. What it is it's one master script and a few others that you apply, and you create an agent job and schedule your maintenance. Now, it has a bunch of parameters you can change. It is availability group aware. And basically, you run it, you schedule it. Now, as a default, the parameters on screen is what we'd go for. On a normal system, just a run-of-the-mill, nothing particularly unique, a standard system, this is probably a good starting point. And what this means is just to take you through a few of them, The fragmentation level 1 and fragmentation level 2 are the two very important parts of this. What that means is it looks for all queries, all indexes, and it looks at their fragmentation. And that returns as a percentage. Now, if they're over 80% fragmented, then this parameter will get used and it will rebuild the index when the maintenance is run. If it's below 80, but above 50% fragmented, then we'll reorganize the index. And you can see that from the fragmentation medium and high. It'll try and do them online first, and that's if you're on Enterprise Edition. If you're not, it'll do them offline, which is your only option if you're on another version like standard. So we're only going to rebuild our heavily fragmented tables. Now the next two very important parts are the last two. You've got update statistics all, and you've got the sample is 100. Now that's basically saying whenever this is run, do a full stats refresh across the entire environment. That has a lot of advantages. There are a couple of gotchas with that, but the statistics sample, what that also means is when SQL Server is creating those histograms and the layout of the data, sometimes it doesn't read all of the data. It'll have a quick scan and go, yeah, this is about it. It's fine. The statistics sample means no, actually go through, look at it all, and build me a proper histogram, please. Now the gotchas with statistics being updated is we're doing as part of this, we're updating all statistics across all tables in the database and all indexes. When you update statistics, any execution plans which have previously been worked out by SQL Server and stored in the plan cache will get nullified. We're starting again when it comes to the plan cache. Now, often you're going to make a better plan next time you run it, but it does mean the first time any queries run, you'll have to create an execution plan for it. It happens automatically, but it does come with a little bit of overhead. You're talking hundreds of milliseconds in most cases of building the execution plan, storing it in the plan cache, and then going again. But it's worth noting it doesn't come without its gotchas. And again, if you've got any particular questions, feel free to get in touch. I'm happy to discuss them with you. But yeah, I'd highly recommend this. Now, depending on your environment, our default would be to schedule this overnight, every night of the week. And you want to do it out of hours because you'll be redoing this, and that's heavy on IO. You're reading them all off disk, rebuilding them, chucking them back, anything that needs to be rebuilt. And that can take hours. So what you'd want to do is run this once with quite high thresholds, see how long it takes in your environment, see if it causes any blocking, because whilst this is doing it, if it's having to rebuild them offline, no other queries can access that data while it's being rebuilt. With online, you're usually fine. It rebuilds them and then switches the data out at the end. So it's quite a quick cutover. But it's not free, it's intense when you run this. If you've got a particularly large system or particularly slow IO subsystem, maybe do it once a week on a weekend. That's very much it depends on your system. As a starting point, most systems, I'd start with these parameters and schedule it overnight or out of hours, wherever your users use the system. For most people, that's within working hours. Okay, so we've got index maintenance done. We've got that scheduled. Now, common mistakes people make with indexing, ignoring the maintenance. We've covered that. You want to maintain your indexes. Over-indexing. And I've mentioned this. If you create too many, that's extra storage, extra data read off disk, stored in memory. Your page life expectancy is going to go down because you can't store stuff in memory as much because you're trying to store more in memory. And also when you're inserting, when I mentioned the inserting into 20 indexes, all of those have to be synchronized. If you're in an availability group, that has to be synced across your network to your second node of your AG. That's all extra work. So that's something to consider as well. If you create too many indexes, you're going to have pain when it comes to write operations and network and disks and what have you. At the other end of the spectrum is under indexing. If you don't create, if you create all your tables on heaps and don't create indexes, your system's going to suck. It's going to run. It's like you're walking through mud. We see both of these. I've seen them both in my career. Aggressively over-indexing or aggressively under-indexing queries, indexes. So we want to be conscious of what we're doing. We want to create as many indexes as necessary, but as few as possible. Kind of find that balance. Brent Ozar uses the 5x5 rough rule of thumb, which is that he wants at most 5 indexes on a table covering 5 columns. Again, very rough, but it's a nice catchy 5x5 to kind of use as an initial guideline. But again, don't live by them. It's not a hard and fast rule. One thing we also see is duplicate indexes or borderline duplicate indexes. And what that means is you've got indexes which are perhaps indexed on the same fields, but with different includes. Why would you have those two indexes separate? Why don't you just have one index which is the same indexed fields, which is what we're searching on, it's what it's in our where or our join, our predicates, but then mash the two in all the includes together, so you're only storing that data once rather than having two separate indexes to produce the same result. And similarly, borderline, where you have one index that's indexed on reputation, and then another one that's reputation and display name. Why have the first one if you've got the second one? You're still indexing the first column the same, you're just indexing an additional one. Does it make sense to perhaps combine those and just have the one index? This is when we come back to it being more of an art than a science. And one thing I mentioned earlier briefly was, for any of you that have looked at an execution plan, at the top you can see a missing query hint where it says that I'm missing an index here. Sorry, a missing index hint. I'm missing an index here, and it could be multiple, but it basically SQL Server says, I want this index. I'm going to run 99% faster with this index, which sounds fantastic, and it may do, but it's worth noting that when you talk about indexing multiple fields, they are indeed indexed in order. So going back to the idea of the users table in Stack Overflow, I want to index, let's say it had first name separate from last name, and it had account ID. So I want to search for all account IDs. Sorry, and no, maybe we use reputation and name. I want to search for all reputations for people called Richard with a reputation over 10,000. So you want to index both of those fields. Now, which one do you want to index first? Because you're going to effectively order by one and then do a sub ordering within that for the second. Now, if I grouped by Richard first, display name comes first. There may be 10,000, 100,000 Richards. I then want to search for, of those 100,000 people with a reputation over 10,000, which might be 100, 10. So if I index them that way around, it would be going, okay, 100,000 records read. And then, oh, actually, I only want these 10. And then I return 10 to the query and carry on. But to do that, I've read 100,000 rows. If I index the fields the other way round, there may only be 1,000 people with a reputation over 10,000. And then within that, there might only be one Richard. Or to be fair, in this scenario, there'd be 6 Richards, 4 Richards. But the point is, the first indexed field in the order means that I'm actually only working with 10,000 rows of data rather than 100,000. So the order matters. And when SQL Server asks for an index, whether that be in the Blitz script we'll talk about in a minute, the Blitz index script, or in an execution plan, it doesn't consider the order of the index fields. It will just take the order in which they are in the table. So if display name came before reputation, it would ask for display name reputation. You need to go in and check the cardinality of your data, which data is more unique, before considering which way you want to index. So don't believe it. Also, I mean, it might get it right by chance, but don't put your faith in it. It's also worth noting that those indexes only requested based upon the where clause predicates, not on joins in the on clause. It won't ask for those. So bear that in mind as well. There may be indexes that can benefit your query that SQL Server won't ask for because it doesn't know. It's not quite that smart yet. So you can bully it. Just be aware of those. May as well take a little break here. Any more questions, Jason? Or any questions, Jason?
No questions, Rich. We're getting close to the end of our time.
Yes.
You know.
Yes. There's only a few more to go. Okay. So doing index analysis. This is the thing you want to do regularly, but you'll want to do as a one-off. Now, many of you will have seen DMVs, index DMVs. They're dynamic management views, and these are the things that SQL Server uses for DBAs to allow them to look at data behind the scenes and make decisions. Now, what you can do is you can query these directly, and you can write complicated queries that do it, or you can use something like SP Blitz Index. Now, this is a tool that's part of the first responder kit from Brent Ozar. It's open source. It's on GitHub. You can submit your own problems and code to it. But basically, you put this on your server and run it, and it will give you a full output of unused indexes, overused indexes, missing indexes, duplicate indexes. It will give you a full rundown of your environment. And then it's a case of reading the links that are in there about what that means for your environment and how you fix it. And you can work through it. It's worth noting, a lot of these open source scripts don't work on Azure SQL DB. And there's a couple of reasons for that. Microsoft, for some reason, like removing DMVs randomly, changing them so nothing's reliable. Also, the stats only persist since your last server restart, and by definition on Azure SQL DB, they can restart your server whenever they want and you won't know. So you can't trust the data in Azure SQL DB. It's great for any other hosting solution, on-prem, AWS, Google Cloud, whatever, but just Azure SQL DB is just something to be aware of. It's a bit of a pain. And you can also, if you're going back to, rather than looking at the server as a whole, if you've got an individual query, the execution plans often will give you some good information to go on. And you may have to look at the XML that sits behind it, but you can get some good index hints off there. I'll quickly move through the end. So there are some particular scenarios, some edge cases, some very specialist stuff that you can use and align with your index. So partition tables. I won't go through what they are, but if you're indexing a partition table, you want to make sure your indexes are aligned to your partitions. Otherwise, you're not getting the benefit of them. When it comes to large tables, again, partitioning, you can create filtered indexes. You can consider column store. This is a very large table. And then also for any sort of data warehousing solution, column store is great. If you're doing big ETLs, you can drop all your indexes, do your ETL and create it later. There's lots of tricks to it. Again, if you struggle with anything, reach out to us. We're happy to help. The last thing I'll talk about is indexing temporary objects. Now, within something like a store procedure or code in .NET or whatever, you can create temp tables or table variables. And you can index these just as you can index a persisted object, so an actual table or an actual index. You can cluster them, you can non-clustered index them, you can do the same. And if you're having performance problems with temp tables, definitely consider indexing them. Now, table variables, you can still index. You have to do it on table creation. You can't mess about afterwards. And table variables have their own gotchas with statistics and what have you. I would tend toward tables if you can, and they're just much more flexible when it comes to indexes. So to conclude what we've talked about, indexes are definitely something you should be considering as part of your system. When it comes to performance, you should be looking at this. It matters. Whether you're an expert or not, doesn't matter. You can start learning. And you can use things like Blitz Index tool. You can use maintenance tools from Ola Hallegren to get you kick-started whilst you're getting up to speed. Doing this properly and learning and revisiting and designing them correctly in the first place can definitely make your queries so much faster. Specifically your read queries, which is 90% of your workload in most scenarios. You read a lot more data than you write, but you do have to do the monitoring and tuning regularly. What that cadence is up to you, but you can't just set it and forget it. You need to go back. So it is a bit of extra work for you, but very much something you should be doing. That's pretty much it. If there's any more questions, pop them in chat. Otherwise, our details are on the website. You can get in contact and we'll be happy to help. Is there anything else, Jason?
We'll stand by another moment or two to see if people post in their questions, but appreciate your time, Rich.
Sure.
Obviously,
Sure.
a very deep topic, and in our preparation for this webinar, internally, we discussed the importance of statistics and that we might do a future webinar on that topic. Usually when we wrap up a webinar, we let you know of the next one, but we're going to take the next few months off. We will probably come back in September with our next round. But for now, thank you for sticking with us a little bit past the hour. We appreciate your time. Don't see any questions, so I think we're done. Rich, thank you.
All right.
Okay.
Thank you. And yeah, if anybody needs to reach out, you know where we are.